Welcome to the final day of our workshop. It's my pleasure to introduce Nielsen from the University of Copenhagen, talking on measuring change by registration.
Yeah, thank you, and thank you, Martin, for inviting. It's a pleasure being here, even though I came a little late. I had to stay a couple of days in bed with a flu in the beginning of the week, but I'm very happy that I managed to be here some of the time at least. Especially also because here it says professor and image group and so on, but actually I've gone over to the dark side the last couple of years, so I'm head of department, which gives me less time to research. So this is like a week. It was supposed to be a week in heaven. It has become a couple of days in heaven coming back to really research here. But so let's go back to the white slides and say this is I'm not going to present you any Excel sheets about numbers and how many students are in the department, etc. So the motivation for looking at in this talk is that we've been working for quite some years on measuring brain changes during dementias, especially Alzheimer's, but also other types of dementias. So this is kind of the driving application that I'm going to use during the talk. And when we're looking at it, there's some things happening in the brain with amyloid, with the tau-mediated neurofibrous tangles coming. Then comes the MRI kicking in, and then comes function afterwards. And the whole idea is to look at this curve to see can we actually measuring these changes along this curve here. So that origins back to Braak and Braak when they were doing the staging of Alzheimer's disease, and Vimuri had a wonderful paper on actually looking at the role of MRI in Alzheimer's disease. So what we all know by now is that the brain is shrinking during Alzheimer's disease. Various parts of the brain shrinks in various speed, especially the hippocampus is involved in it. Here we have a part of the ventricles, and we are looking at here the flow field over the deformation field over a period of a year, and what we want to measure is the change that has happened over this year. But in practice we are in the situation that we have the images are non-quantitative intensities. They vary from time to time depending on scanner, how much liquid is there in the patient on the day, etc. So there's the bias field showing up, there's image noise, and there's image discretization, and we have to factor in all these things in order to be able to measure in practice. And just to tell you a little about it, if we're looking at the hippocampus in a high resolution clinical scan, this is about 3,000 voxels, but 1,000 of those lies on the surface of the hippocampus. So it's like a third of all the voxels that are of these Lego blocks that are on the surface. So you can see if we want to measure the difference between the normal aging that has a loss in the hippocampus of 1 to 2% per year and the Alzheimer's that has a loss of 3 to 5% a year, we are definitely in the subvoxel regime. We need to measure differences that are in a tenth of a voxel approximately. So that means that all the nitty-gritty detail about how do we handle discretization, how do we handle the noise, etc., becomes really important. And Mark, yesterday you showed this deep learning approach to registration, and you said you had a median difference in 0.3 voxels, so there was no idea in improving things. I would say if I had an error here in 0.3 voxel, and if it was biased in some way, that error, then all my signal would have gone. Of course, if it's totally random, then you can average over the full surface and you will still have a signal. But we do need this very high precision in order to tell the difference between normal aging and Alzheimer's. So that's the motivation of the talk. And then we go into the usual stuff. We do a segmentation of the brain into the various compartments at baseline and follow-up. Then we do a rigid registration from baseline to follow-up and vice versa actually. And then we do the registration, and that is we do normalization. We have to look at the transformation model, the similarity measure, how do we do the optimization, how do we do the regularization, and finally in the end, how do we measure the change from this deformation field to minimize the numerical noise that we are adding to the whole procedure. And let me start in this end by just looking at how do we actually measure the change of volume or the change of shape based on deformation fields. So normally, so this is a voxel, and it has been here I've only deformed the corners, so I'm assuming for a second that it's still planar triangles after it has been deformed, and then I can easily compute the volume of this voxel. So that is what people are doing. They're doing tetrahedral measures of it, and as long as you're doing the triangular, making the triangles in a consistent way from neighboring voxels, you get a very precise result coming out of this. So if we look at it, the standard way people have been doing is taking the Jacobian and then integrating it over the area you're interested in order to find the volume. So if we are looking at it in that way, we can also make it into a surface integral with a Gauss theorem. We look at the surface integral, and then we can take some vector field that we probe to the outwards normal with, and then if, for example, we make that vector field just to an x00 vector field, we exactly get the volume out in the end. No magic, a little simple math. And this here, measuring this one, we can do by just looking at the area of the triangles projected in the x direction in this case. So that's very simple procedure. We can do it voxel per voxel, or we can take a little numerical noise out by not having all the triangles that are the same on neighboring voxels, so we only do it on the surface of the thing we're looking at, getting faster computations and the same precision as doing the tetrahedral meshing. So just as a little example, we take a 2D image. We had a blurred squared. We are doing a shearing of it, and then we are looking at the error in. So we know that there's no change in area here, and we are just looking at what is the area if we are doing it by this, looking at the volume of the cubes. It is down in percentage, whereas if we do Jacobian integration, we get an error that is increasing with the shear due to the numerical integration noise. We could have used many other rules for doing the Jacobian integration than just doing left point. We could do midpoint, trapezoidal, or Simpson's rule for doing the numerical integration. And the order of approximation we have looking at what's happening here when we have the discretization distance is h. That the precision is, if we go up to Simpson's rule, we have an order of h to the power 4, just like we have with the tetrahedral meshing here. So you could see why we could as well go with Simpson's rule. But if we then look at what happened under noise with these two different ways of doing the integration, we have made a small example here. We have a deformation field which is just with a Gaussian profile, so we can compute analytically how should the volume change. And then we added a little noise with a random phase and a random frequency in some amount, and the higher, and then we done it 10,000 times, something like that, measured the change of the volume. And here you see the error growing with the noise level, and here we have Simpson's rule that it grows actually linear in the noise because it's estimating the derivatives locally. So it's very prone to noise that comes as a little flickering on top. So the best way to measure the change depends on whether you're in a low noise regime, then you should go with Simpson's rule, or if you're in a high noise or higher noise regime, then you should go with the tetrahedral meshing or the surface integration. In that way, that's the most precise way of doing it. So I'll come back to results on that, but just a sidekick saying that we can, of course, similarly with numerical properties, look at all moments of the shape. We can just probe with different vector fields and get different moments out. So this surface integration, we can go to all moments of the shapes, and we can solve analytically on the planar triangles for these polynomials. So everything is fine and good for also other things than measuring the volume change. So let's go back to the driving application and then look at some results. We are taking here. We have tried it on many different data sets, but now I'm going to show the examples of this now. Very standard data set. So that's the 2-year data set from ATNI. The 504 individuals they had with complete 2-year scans back in 2012. And we're only looking at the normal controls and the AD group, and have taken the MTI out just to look at what is the difference between these two groups, just as a you can say as a nearly cartoon example of what's happening in real life. So here comes a very busy table. If we start by looking at, if we were just doing segmentation at baseline and follow up, we are looking at the whole brain, the hippocampus, the ventricles, and the medial temporal lobe. You see that, so this is because it's segmentation based on baseline and follow-up, then it's unbiased in the amount of atrophy we get out of it. And you can see that the hippocampus has minus 4% in volume with a standard deviation of 5, and the normal controls at 1.5. So that compares to the numbers we have seen in literature that I gave on the first slide, 1 to 2% and 3 to 5% here. Of course, then we can go to the Jacobian integration. Here, now let me just finish this row with the hippocampus down here, and then we can look at the area under the curve of how to separate out Alzheimer's from normals, and then we can look at how many standard deviations are the two mean values apart. So this is the nonlinear statistics or non-parametric statistics. This is the linear statistics, so to speak. So this is the essential parameter going into a t-test on the difference. So and if we go to just this changing the way of how we do the numerical integration, changes the noise quite dramatically, and we also see that we get a significantly higher cones D on the hippocampus and on the whole brain, just by doing the numerical integration slightly different, because we are looking at such small deformations or such small volume changes. So that was the first step of how do we actually measure. I could also go to the different ways of doing integration, Jacobi integration, and we basically get the same results. So we are in the regime where the noise is so high that that the symptoms rules is actually not better than midpoint or trapezoidal integration. We're getting exactly the same results here. And we can also see that especially for the small hippocampus and for the whole brain, where there are also more difficult paths of doing the deformation field, it matters, whereas the ventricles, which are extremely easy to get a very good smooth deformation field for, because they have such a clear contrast in the images, so the registration is not as noise prone. We also see that there's much less difference. So then let's go. So this was assuming we do have a deformation field. Then let's go to figuring out how do we obtain this deformation field. And this should come as no surprise for you that we are looking at a deformation of an image. We have a similarity measure, and then we are doing a regularization also. So we're going to look at these parts. So if we are going into the similarity measure first, keeping all the geometry out of it so far, we are using the normalized mutual information that is essentially dependent on the joint histogram of the two images. We place the two images on top of each other, and then we need to measure the joint histogram and differentiate that with the parameters of the deformation field in order to find the optimum. So there are two dominating ways in the literature of how to estimate this. One is with a Parson window, and the other one is the so-called partial volume way. Let me just illustrate this here. That when we place the two images on top of each other, we take a single point. It does not any longer fall. It's not coinciding grid points any longer because we have been performing the registration. So the point falls compared to the grid of the other image, here in the middle of a pixel. And then the partial volume effects just say that we take a weight comparing to the area of these on 3D of the volume of these rectangles here, and we plot that into the histogram that we have the intensity here, and we divide it over the intensities in these four corners with these weights. So that's the partial volume, whereas the Parson window is using basically just saying that we are placing a Gaussian for each or some other Parson window function around the intensities and put them in, so we get a smooth joint histogram. This one is very nice to estimate fast. This one has much nicer properties in terms of differentiability, etc. So this here is a special case of Kundering's locally orderless images. So I'm going to take a slow walkthrough of these locally orderless images. So here we start with an original image. Here is what the histogram of this noise image look like. Then the first step is that we blur this into a Gaussian scale space. So now the image has changed to being this image instead. And the histogram of that image looked like that. Now it has been much more centered around the mean value here. Next step is that we are looking at blurring in intensity space also, since we have discretization of intensities. So we blur in intensity also, and here we get a number of different isophotes in the blurred image, and you can see for different values here they have been drawn, and these are, except for generically, these are nice smooth curves. So let me. So if we are just looking at one single of them, since we have been doing this blurring, we get these soft isophotes in the images that look at this one down here. It becomes quite stretched out spatially because it's in a very flat area of the image here. So we get this uncertainty in both. Yeah, let me jump over some of these. And next step is that we are actually then also going to look in a local neighborhood in the image with a Gaussian profile again. And then we get a histogram in this position like this, and in a different position we get a different histogram like that. So we have these three different blurrings. We blur the image, we blur the intensity axis, and then we are looking at the histogram in a Gaussian neighborhood. That's Kundring's locally orderless images, and now we can look at these local histograms at various intensity and spatial scales, and everything is nicely differentiable and so on when we're doing this. So of course we can do that for the joint histogram also. Then basically the integrals becomes a little longer, more nested integrals, but it's basically the same thing. So let's look at how does it. So we have taken how it works in practice. The difference between this Parson window and the generalized partial volume, that is the fast numerical way, that when I take an image and translate it over itself, looking at the displacement in pixel, that the Parson window gives a much nicer peaked image compared to the generalized partial volume. So it's easier to optimize along the red curve here than along the blue curve, especially when we start to add noise, etc. So that's basically the story of, by taking the image, blurring it, but also blurring in the intensity axis, we get smooth joint histograms, and we can do numerically stable integration of that, and we can handle derivatives of the mutual information in that way. So only problem left is that we have these Gaussians with infinite reach out, so every point get dependent on all other points and so on. So from a computational point of view, it's terrible to do that. So the thing we need to do is to use filters of compact support in order to make it work in practice. Otherwise, your speed up mark from 7 hours to a few seconds. We are in the hours regime because we haven't used the deep learning trick, and that hours would become months instead if we were doing the full normalized mutual information in this blurred version. I just so we are doing it by B-splines to get this compact support. That's maybe not the best choice, but that's what we did at this moment, and it does help. I just wanted to come back to this If we're using this, that is the most popular because it's the fastest, this partial volume effect. Of course, it's not symmetrical either, so that if we're measuring from the one image to the other, so the optimum lies different places also. So there are many reasons for not using this. The only reason for using it is that it's fast. So that was basically the part about how do we measure the normalized mutual information. Then let's get into the transformation model. And that's there I can skip a little more of the explanation because many of you knows this much better than I do. But basically we are going into having the one parameter subgroup of the diffeomorphism with the stationary vector fields. So we are estimating a vector field and we are integrating it over time in order to find the deformation field. So that's the normal stationary vector fields. And we are going to parameterize these vector fields also using compactly supported functions in order for being able to compute this in real life on real images. And then we are going to do it in a multi-scale fashion. So I'll go through these steps. So this is just the flow field and then the integration of it. I'm not going into how we are actually doing the integration. I skipped that part of the slides here, but we do have a time adaptive way of doing it, so that depending on the curvature, we are subdividing time finer and finer locally in the image, so that we can do it fast and precise. We tried with scaling and squaring, but you can think about it in a little moment that we are estimating things with basis functions, and we need to, whenever we have been doing scaling, one step of squaring, we are projecting back to the basis functions, which means that we go back into the same subspace living in there. So we are squaring and then we are projecting back into the same subspace. So for this, working with the representing the flow field with a compactly supported functions, it doesn't make much sense to do scaling and squaring because we get back to the same basis functions whenever we have been squaring. So the numerical noise due to this projection step becomes larger and larger and larger in scaling and squaring. So it essentially it nearly breaks down doing scaling and squaring. So we are using a forward Euler scheme with adaptive time stepping of it. Then when it comes to the basis functions we're using, you know that normally in LDDMM, etc., it's defined by a differential operator, the smoothness term, the norm that induces a norm, and then that again induces a kernel. And if L is a differential operator, that kernel has infinite support. So we cannot just, for computational reasons, go ahead and use these. We want to get to the kernels of compact support, but we still want to be in choose a reproducing kernel directly. So let me just jump that one and then jump directly to the Wendland kernels instead of B-splines that people are normally using to represent the flows. We're using Wendland kernels. They have this property that they are actually reproducing kernels, so that that they do induce a norm, etc., and things are from a mathematical point of view nice. So you can say, but are they also from a numerical point of view nice? So all these, whenever I've been presenting this in the more practical communities, people have been saying, yeah, that's all math, but does it work? Why does it work? And this is kind of the reason why it works. Here we are looking at the Fourier transform of the different kernels. We have the Gaussian kernels that has this nice, on a logarithmic scale, nice second order parabola here. And then if we are looking at the cubic spline, you can see that it goes down, and then it goes down and becomes negative, and so on. It has a lot of side lobes, the B-spline, and that is the reason why they're not working in practice, because you amplify some negative, so you're averaging out some frequencies, negative and positive frequencies, when you're using them, whereas the Wendland kernels, they are nice and positive. They do have a longer tail, of course, than the Gaussian that has the the same spread in the spatial domain, has the most compact function in the Fourier domain, but they have much nicer behavior than the normal splines. So we're using the Wendland kernels. Then we are using Stefan's work. Oh, I can see you can hardly see it here, but we are using the kernel bundle framework from Stefan, where you can show that you can take the kernels at the various scales and just take the metric on the various scales and add up the metrics from those to make it work. So we can do it in a multi-scale framework, having small scale and large scale kernels, and having a simple metric still that is just adding up the metric on the various scales, making things work nicely. So then we get into the optimization here. We have the norm from the kernels. We have the locally orderless images, mutual information data term here. Then we add an inverse consistency term here. And actually, you can see that this here is measuring all the difference in the one end. So we are adding the symmetric part of this, where we are going, instead of going from A to B and measuring in the one end, we are measuring in the other end also, but maintaining the same deformation field. So we have a forward and a backward deformation field, measuring the differences in both ends of the registration to have the symmetry, and then we go with a standard BFGS optimizer running on this, and then we get results like that. You can see our old results are down here. When we are looking at the whole brain, we are jumping a little. The hippocampus is basically the same, so it didn't improve here, but it did improve on ventricles here, but not on the medial temporal lobe. So that was, of course, a disappointment. All these steps to do things better, that we are, we could argue we are slightly better if we put in the positive view of it, but it turns up very easily that everything comes from the intensity normalization. All the error comes from using standard way N4 algorithm to remove the bias field from the MRIs. That is doing it in a way that is not sufficient. So next step is you can see here is an example where this is how the change map is coming from these images, and that is due to that the bias field is not removed properly by the N4 algorithm. So the next step is to jump in and say we also put the bias field modeled by a bias exponentiation of some positive or of some field here, exponentiation to make it positive. Here we represent it by B-splines again. We can also say that we want it to be smooth, so we are putting in a regularizer on it, and we are putting in a symmetry term saying that we just so the images don't drift off with the bias field, so if we're going up in the one image we need to go down in the other image basically. We throw also all this into an optimize over these parameters also when we are running the registration. So we are estimating the bias field at the same time as we are estimating the registration. So this is just another set of variables to solve for. And then luckily we are better off that we now have improved also where it really hurts on the hippocampus, which is a very important structure in Alzheimer's studies, that we get an improvement, and in this case also for the, at least for the cones D, a significant improvement on this data set. So that's that is the next story about putting in also the bias field estimation. And if we then compare with some of the method on the same data set, it has been run not by us but by other people that have been producing other methods. So here's the comparison to ants and to LCC demons here, and for me to see the major steps that we have performed here has not been coming from trying to do all the numerics of the flow field, of the deformation fields better, because that step actually didn't give us the improvement. It was including the bias field estimation in doing that simultaneously with doing the registration, and then doing the measurement based on the flow fields based on not Jacobian integration. That's the two important steps here. So that's basically the story through these various steps. I skipped over the optimization and some of the regularization part for the sake of time, but I wanted to highlight the points that I do believe actually matters when we want to use these methods for measuring change. So thanks for your attention, and thanks to my collaborators that did all the work.
Questions?
So can you come back to the Jacobian computation you presented? So I missed the definition of the method CP, the improved method CP, and so at the very beginning.
So
yeah. So VCP.
Yes.
So
So this is just numerical integration of the Jacobian. And these are different ways of doing the numerical integration based on the midpoint, trapezoidal rule, or Simpson's rule. So these are Simpson's rule is normally considered the most precise way of doing it.
And VCP, so can
yeah, so that is the method where one way to look at it is just that we are for all the cubes in the image we are doing at one way to look at it is it was a tetrahedral meshing, but we're doing it with a surface integral instead. And then we are assuming that all the triangles are linear afterwards. So we're just saying that these are planar triangles, and then we're computing it. Of course, they're not planar given the deformation field we have. So we do have an error based to that they are in reality curved, and that is in the order of the discretization step size and the power of 4, just like Simpson's rule. So that's
Okay, thank you.
so.
So was it standard in numerical analysis to develop this kind of integrators? Is it a standard method in CP, SCP? Is it
No, that's not standard, but it's just the but it's you can say in our community it's nearly standard using Gauss theorem to change the volume integral into a surface integral.
Yes.
So that's it's nothing fancy, but it just has nicer numerical properties. And also, if you're going for speed, you don't need to go for the for all voxels. You can just do it on the surface of an object if you want to do that. So you can reduce complexity if you want to do things fast. Also, so it's very simple. So everything here are just very simple steps, where some of them really do matter when you look at the precision you get out in the end. And some of them matter less. And I think this integration here and the bias field correction, integrating that in the deformation field estimation were the two most crucial steps.
Okay, thanks very much.